Alright, so here's our spring break lesson for the day. I'm going to try to keep this one fairly short. There's going to be two videos that I'm going to post for you, one on slope fields and one on separable differential equations. Now, this is in section 6.1 in your textbook, and so we're just going to do, we've already talked about it a little bit, we'll just do a quick overview on this, and then I'll give you some things that I want you to work on. One of the things that you want to kind of review for yourselves is you know that your anti-differentiation, me telling you to do an indefinite integral, and then if I solve a differential equation to find a general solution, that these are all pretty much the same process. Now, up to this point, we've kind of only been looking at differential equations where they're functions of a single variable, and that's going to change a little bit in this section. We'll talk about what to do with that. But when they're functions of a single variable, then we pretty much know that we can put this in differential form by moving the dx over and then integrate to find the general solution. It doesn't matter if you have a t in it as long as you're integrating with respect to t. So this would be dh dt. This is actually a second derivative, which is fine. This is called, anytime you have the first derivative, it's called a first order differential equation. Anytime you have a second derivative, it's called a second order differential equation. Okay, and then if we all wanted a particular solution to the differential equation, then we had to have some type of an initial condition, and you had to find C using that initial condition. Now, we're going to look at some differential equations that are not necessarily explicit functions of a single variable. And there are also going to be some differential equations that we cannot solve by analytic methods. And when we can't solve them by analytic methods, what we want to do is we want to have this idea of how can I come up with a solution. And the idea is that we're going to graphically solve them. We're not going to be able to find the actual formula for the antiderivative, but we can find this formula by visualizing what it would look like on a graph. So a slope field is nothing more than a graphical general solution to a differential equation. It is a way to find the family of antiderivatives for a given differential equation or derivative equation. Okay. Now, one of the things, like for example, we want to take a look at, if I have a derivative function like here, dy dx equals x squared. What I'm basically giving you, when you say dy dx, you have to remember that that's nothing more than the slope at any point xy. So I can pretty much plug and chug, and at every single point in the Cartesian plane, very tedious, I can plug in the coordinates of the point, and I can calculate the slope at that point. And what you basically do in your slope field is you're going to draw a little tiny little segment that is representing the tangent line at that point. And what that gives us is this idea of kind of a, in graphical sense, where the antiderivative function is going. Okay, it kind of gives us the motion of the antiderivative. And a lot of times when we are, it's easy to kind of think about this as a derivative like this one where we only have it as a function of x. The only difference between all of your antiderivatives is this different c value. And so they're really pretty much just parallel antiderivatives. They differ by a vertical shift. Once we start getting into derivatives that are not functions of only one variable, that may not be exactly what's happening, and we'll kind of start visualizing what's going on with those as well. Okay, these are also called vector fields, flow fields, or direction fields, and these are a very big application of calculus and the use of these slopes. Kind of give you the idea of a flow of a things like oil fields and things like that. So you can kind of get this idea of where things are headed. All right, let's take a look here and kind of some notation. Make sure that when you are doing the slope field, you pretty much are going to assign a small piece of a tangent line. And when we say small, it's small. You really want to make just the smallest little mark that has the correct slope, okay? Now notice that we're going to start to use this notation here. We're going to evaluate the slope at a point x, y. You can use this f prime of comma x comma y to give this idea. That'll be the notation we're going to use. You want to make sure that slopes of 1, slopes of 0, slopes of -1, and vertical slopes are going to be the ones that you really want to get correct when you're doing this. And then the rest of the slopes that you're going to be graphing, you kind of just estimate them relative to your 0, 1s and your vertical slopes. And then just to remind you that, and this is going back to something from before, to get a slope of 0, when you calculate your derivative, your slopes, you need to get 0 over non-zero for your 0 slopes. If you get vertical slopes, dy dx has to end up being non-zero over 0. Okay, so that's just to remind you, here will give you a vertical slope, this would give you a 0 slope. Okay, so now pretty much in the example that we're looking at, which is our derivative was x squared, you pretty much just plug in your points. At 1, 2, the slope would be 1. At 5, 3, the slope would be 25. At negative 3, 11, the slope would be 9. So like if I'm sketching these little slopes, you pretty much, and it's going to be, you're like, okay, slope of 1. Slope of 25, well, that's almost essentially vertical. Slope of 9, almost vertical, but maybe not as much. Okay. Now, obviously, it's going to be impossible to do a slope field. They're very tedious. You don't want infinite points in the plane. Usually what they're going to do for you is they kind of give you a picture like this, and they say, estimate the slope field at the indicated point. So pretty much, and usually on the AP, they'll go ahead and they'll give you points where they want you to calculate the slope field. And so, like in this one, we'll go through it. We're going to do it at all the integer points. I'm not going to put all the dots on there. Just pretend like there are dots at all of these places, and we're going to calculate our slope field. All right. So we have our dy dx equals x squared. Now, the first thing you want to notice about this is that this is a slope that is a function of x only, that it does not depend on y at all. So that really makes it easy for us kind of as we are kind of calculating this. Like, so if I go here, I'm on the x-axis, or let's do on the y-axis. On the y-axis, every single point has an x-coordinate of 0. So when I plug in 0, 0, the origin, I'm going to get a slope that is 0, and so I would draw a horizontal line. But then notice I get exactly the same thing at every point on the y-axis, because at every point on the y-axis, x is equal to 0. It doesn't depend on y, it only depends on x. And you'll notice that in this vertical fashion, all of these are going to be parallel. If I look at the point right here, 1, 0, the slope is going to be 1. So I kind of estimate and I draw in a 1. What's the slope going to be up here? It's going to be 1 as well. It doesn't matter that the y changed because my slope is not dependent on y. So we pretty much draw in our positive 1 slope. If I put in negative 1, oh wait a minute, that's going to be positive 1 too. So we go ahead and it'd be helpful if I draw it positive 1. Draw in your positive 1 slopes again. Okay. So sometimes, because of the pattern that you have, it's going to be fairly quick to draw. And then if I'm over here at 2, 0, well then I would have a slope of 4. Well, I just need to make sure that it's steeper than the one that came over here. I mean, it's what we call relative slopes. So, and these are all the same, so you try to estimate even though you're going steeper. And then the same thing over here, you're also going to get the 4, and so you want to try to make it the same as the one over there, steeper and going in. Okay. Now they're not going to ask you to draw these for much more than maybe 9 points. That's going to be the essentials that you're going to look at. And so now what you're doing here is you're giving yourself this idea that the general solution has to follow this flow. And so like suppose I want to say that go through this point right here. So if I wanted to draw a solution that kind of starts from here, you say go with the flow. As I go with the flow and heading this way, I need to kind of follow the flow of the slope field. And as I move this way, it seems to be getting steeper and steeper. And then over here, now see how I'm going down? So I might be going, well, let's go down and then follow the path on this way. And you can kind of start to see the flow of the field. And this would be a particular solution to this. If I pick another point to go through, say here, and follow the same thing, and you can kind of see in this that what you're getting are essentially your parallel solution curves. And we pretty much I call this the squint, eyeball it, and go with the flow method. You kind of just pick what point you want to start from and just follow the flow that you're going to be working with. Okay, now of course it's fairly straightforward and easy for your computers to get your derivatives, and so a lot of the times if you had to do a lot of these, you would pretty much have the computer do it for you. Use Mathematica. I did put a link up in the It's Learning. That's just a generator for slope fields. You put in the equation, you say where you want them, and it'll generate slope fields for you. And we'll take a look at some examples of this. So if we could continue, okay, to create the slope field and using a computer, this is kind of what we would get. We've kind of expanded out because we would never do more than, 5 to 9 points by hand because it's pretty darn tedious. Now, like I said, you want to make sure that you have all your slopes of 0, 1, and -1, and your vertical slopes spot on. Those are the ones that are really going to check, and then the others you kind of make them steeper or less steep depending on the slopes that you're looking at, and you just kind of get close for the rest of them. And again, you can see here that it appears that we kind of have this little cubic fashion looking at it. Now, kind of going back to our differential equation, dy dx equals x squared. This is what we call a separable differential equation. And the reason it's separable is because what we can do is we can put it in differential form. We can separate it so that your dy equals x squared dx. I have y on this side, x is on this side. I've separated the y's and the x's. And when I get it to that point, this is an example. We're pretending we don't know how to anti-differentiate this, but we actually do in this problem. And if I were to find the antiderivative of dy is y, antiderivative of x squared would be 1/3 x cubed, and plus c. And then if you were to graph this class of curves, you could see that you've got the nice cubic curves that are the solutions to this, shifted up or down because of the plus c. And so the slope field is a visualization of this solution to the differential equation. It's a graphical way to find a solution to the differential equation as opposed to an analytic method. All right, let's take a look at example 2. We want to sketch the graph of the solution to the initial value problem. I'm going to go ahead and change. Remember, y prime is the same as dy dx. And so now notice that our slope is not a function of x only, it's a function of both x and y. Now we could just start plugging and chugging with points, but we're going to kind of do this in a more organized fashion. The first thing I would think about if I was graphing is when is the slope dy dx equal to 0? Okay, I would ask myself that question. And in this, it's fairly simple. It would be when x equals the opposite of y. And so if I was looking at, for example, 1, -1, that would have a slope of 0. So we would put that. Or 2, -2 would have a slope of 0. But then so would your -1, 1. Your -2, 2, and then what about 0, 0? Oh, that one would too. And notice in this one, we have parallel slopes going on the diagonal. Okay. And then at that point, you're like, was there any time that you have a vertical slope? No. So there are no vertical slopes. Okay, we don't have any division by 0 in this problem. And then we just start playing around with it. If I were to plug in, say, 1, 1, I would have a slope of 2. Okay. Before I put the 2 in, is there any place where I have a slope of 1? Say 1, 0. Let's do that one and get my slope of 1 in, so that way I have a reference point. And then I'll come over here and I'll go, well, if I'm at 2, 0, that would be a slope of 2, so we'll make that just a little steeper. And then over here I'd have 3, 0, I want to make that a little steeper. Over here you can do the same thing, except now we're in the negative direction. And then a little steeper, our 2 and our 3. We kind of go through in this fashion. And like I said, it ends up being fairly tedious. Here would be 0, 1, which again would have a slope of 1. And then I go, oh, wait a minute, that's the same as here. What about this one? If I have -1 and 2, oh, that's going to be a slope of 1 as well. and then another slope of 1 here, and a slope of 1 here. So you start to see a little bit of a pattern going. Maybe let's test here, because this one had a slope of 2. If I go 1, 1, that has a slope of 2. If I go 0, 2, that has a slope of 2. We appear to be following that diagonal. Here, if I had 3, this is 2, 1, that would be 3. This one would be 3, kind of working our way up. Over here, this one would be 3, 1, so 4. Oops, maybe make that a little bit steeper. And like I said, it all has to be relative. This one would be 5, so even a little bit more steeper. This one would be the same as this one. And you kind of work your way around getting your picture. This would be 0, -1, so now I have a -1 slope going here. On that one would be a -1 slope. That one would be a -1 slope. That one would be a -1 slope. Over here, -3, 1 would be -2. So we kind of follow the pattern there. Here's one would be -3, follow that pattern. This one would be -3, -1, -4, a little steeper, and then -5. So there you go, we've got a nice picture of our slope field. They want the initial condition is 0, 1. So over here, if I wanted to graph that, I find my 0, 1, which is right here. So that's the point that I want to go through. And you do want to make sure that you kind of follow the flow. You want to put that point on. Now from here, I look to the right and I see that, well, it looks like the flow goes up. So I'll kind of head up in that direction, put a little arrow on it. And then I come here, right here, you hit a horizontal slope, which means there's probably going to be an extrema. So I would turn around somewhere in here. You're going to come down because your slope is decreasing right here. I'm just trying to get rid of that little segment. You would come down, you would probably have a turnaround somewhere here, and you're like, oh look, it tends to go up again. So we would kind of follow it in that fashion. When you see a line like this is kind of an indication that there might be some kind of a slant asymptote going on in the problem, and that would kind of give you the trend of where you're going to head out when you're looking at it. Just to kind of show you a few other curves on this one, what if I gave you an initial condition and I wanted to go through -1, -1 is my initial condition. So that would be right here. And so the idea is, well, we must be going up, follow the flow. And then this side's coming down. So you kind of end up with this. That might be your solution, looking at it. What would happen if I were to, let's try a little pink, if I said my initial condition was -1, 0, that would be here. And you're like, well, what do I do? Oh, right, I'm right on that line. You actually can have a solution that looks like this. All right, and this is an example where you might be going, wait a minute, these are not all vertical shifts of each other. And where are we seeing that there is going to be a difference in all of these equations of c, but because this is a function of x and y, the effect of that c is not just a vertical shift anymore, because it wasn't y as a function of x. And so you will start to see things that look like this. Now, the question you might have is, can I actually solve this differential equation? Well, let's take a look at it analytically and let's see what we have. So we have dy dx is equal to x plus y. So I'm going to try that trick of separating, okay? And you're like, okay, what do I want to do? I need to get the y's on one side, the x's on the other, and I need the dx over with the x. Now, if you start to do that, you're like, okay, well, let's subtract the y over. So I get dy dx minus y equals x. And you're like, okay, but I'm not separated yet because I still have the dx over here. And you're like, well, why don't we multiply both sides by dx and let's move that over. So dy minus y dx equals x dx. And you're like, oh, wait a minute, I still have a problem because there's this dx still on this side. And we can play around with this as much as you want. And what you'll see is that this one is not separable. This is a non-separable differential equation. That does not mean that I cannot solve it analytically. It means that in AB Calc, we are not going to have to learn the methods of solving this. There is actually an entire course on differential equations that you would take when you go to college, and that course would look at all the different techniques for solving things that are not separable differential equations, and which we don't have to worry about because we're only going to be doing the separable ones. So this is not something that you're going to be able to solve analytically, but that's okay because we can visualize the solutions by looking at the slope fields. Okay? All right, so let's go over to the next page. So another example, here I have my slope as a function of both x and y, and so I want to go ahead and just plug and chug. You get something, I only have this set of 9 points to do, so let's see. When will I have slopes of 0? Is it possible to have slopes of 0? Well, sure, as long as x squared plus y squared equals 1. Maybe let's try over here at 1, 0. 1, 0 would have a slope of 0. Let me put myself in a color you can see. So we would have a horizontal slope here. If I'm at negative 1, 0, that would have a horizontal slope. If I am at 0, 1, that would have a horizontal slope. If I am at 0, negative 1, that would have a horizontal slope. If I'm at 0, 0, 0, 0 would have a slope of negative 1. So we put that in going in our negative direction. If I am at 1, 1, that would end up being a slope of 1. So that would be in this direction. If I am at 1, negative 1, well, that would still be a slope of 1. Negative 1, 1, slope of 1, and slope of 1. Now, I will say that kind of in this one's a little difficult to kind of visualize what's going on. You know, and the idea is we really don't have enough points to see. You're like, well, what's craziness is happening? If I want to go through the origin, which would be right here, you kind of go, all right, well, it must go up, but at some point, because of this, it's going to have to turn and come back down. But then I'm going to hit this, and you're like, well, what does that mean? At some point, I have to turn and maybe keep going. I have to have a 0. See, that starts to get a little difficult, you know. And so the idea is a lot of times with slope fields, more is better because you've got to have enough of the points there to see the flow. And a lot of times, you know, they'll make it so that you have enough to see the flow. And this is kind of a crazy one with a lot of things going on here. And so the idea is the more tangent lines that we draw, the better the picture is going to be of the solution. And the idea is that you don't want to really do all that by hand. Now notice I've kind of zoomed out here. This was generated by a computer. We do have a little bit of craziness going on here in the center, and that's because there's a lot of turns going on. But now if I want to draw my solution through the origin, now the flow is a little easier to follow. I'm going up, and at some point I'm going to turn around and then come down and then follow the trend heading in this direction. And then the same thing here. It looks like there must be a turn of some sort coming up and then following the trend in this direction. So you can start to see kind of more important to have a few more points. And that's why we're going to use computers to really kind of see what's going on. And then here are some more examples of some changes that are being made based on the constant that's added. And again, this is one where it's dependent on both x and y, and you'll notice it's not just a vertical shift anymore, but there's a little bit of change that's being caused by the constant that's being added to your solution of what it's affecting. It's actually causing it to have these extra little turns in it as opposed to more of a cubic fashion that you're looking at. All right, so let's take a look here at this. These are some of the things that's more like what you're going to see on the AP, which is this idea. You'll see this in a lot of matching. A lot of times what you want to do is you want to match the slope field with the equation of the general solution. Now this should be the easiest of all of them because remember, the general solution is what you're getting a graph of here. So you're basically going to look at this and go, all right, let's say I kind of sketch in a representative one and take a look at it and then go, hey, what does that look like? Well, that looks like a trig function to me. And it looks like a sine function. So you can very quickly, it's like almost just knowing your parent graphs, come down here and go, well, that one clearly has to be F because this is a picture, the solution to the differential equation is a picture of the antiderivative, and they're asking you to match the slope field with the antiderivative that you're basically seeing. Over here, if I had to guess on this one, again, I would draw kind of a representative one in to kind of see what's going on. And it kind of looks like it's following. Oh, that looks pretty cubic to me. Now, your choices when you see this, because you do have some vertical tangent lines over here, could be a tangent of x, but then I noticed that's not one of my choices. So it must be kind of along the cubic lines, and on the cubic lines it must be out of my choices D. So this is kind of the easiest of the choices where they give you the slope field and say find the general solution. It's nothing more than, hey, know your parent graphs from Algebra 2. That's a horizontal line, that's a slant line, that's a parabola, cubic. Your 1 over x squared would be this fashion where you're looking like that. Your log of absolute value of x is going to be something along these lines, and your cosine of x, kind of have your max in the middle. There's your axis. So you kind of just know your parent graphs and you pick the one that goes with the flow. Then we come down to like example 5. We want to look at the slope field from the differential equation, and now we're looking for the specific solution to the differential equation, which is basically saying we're going to let c equal 0 in this. You kind of look over here, look at the trend, and you see that you kind of have something along these lines, and then you go by process of elimination. Clearly not going to have not a parabola. E to the x does this, so it's not going to be that one. E to the negative x is your exponential decay. It looks like that. Not that one. Cosine of x, got to have that fashion. Not that one. Natural log of x is our only choice. Okay? Easy. Moving on. Now this is a little different. Now we're going to match the slope fields not with their general solution, which is the picture of. We need to match it to their differential equation. All right, now there's a couple of ways that you can go. You can go from graph to differential equation, or you can go from differential equation to graph. Let's take a look at this one. Now what's important about this is what you're really going to do is you're going to look at where the slopes are 0, the slopes are 1, -1, and vertical. That's going to be the key here. Now you'll notice here that the slope, dy dx, is equal to 0 when your y is 2. Okay, so we're looking at something that has a slope of 0 when y is 2. And here, it's not dependent on y. All right, I also look at this, and you see that, look, see how these are all kind of parallel going in the horizontal fashion? That it kind of doesn't depend on the x value, okay? It looks like the slope only depends on y, because of this little fashion where you have all these little parallel little slopes going in this horizontal fashion. So immediately when I'm going to match, I'm looking for a slope equation that only has a y in it. So pretty much I know it's not going to be 1, 2, 4, 5, oh look, or 6. The only choice that's left is number 3. And if you check and you go, okay, what was 0 when it was y was 2, and you're like, hey, that works out. I would also make sure I check and go, well, let's make sure above 2, when y is greater than 2, all of my slopes are negative. When y is greater than 2, are all your slopes negative? Yes. And when y is less than 2, all of your slopes are positive. And when y is less than 2, then you end up with a positive slope. So we're good. So we're going to match A with 3. Okay. All right, let's look at the next one, and let's work from the equation and then go to the graph. So here I have the slopes, and I might ask myself, when do I have 0 slopes? So dy dx equals 0 when x is equal to 0. And you're like, okay, well, and notice that this depends only on x. So we're pretty much looking for something that doesn't matter what the y is, which means that my parallel little slopes are going to be all vertical from each other because the y's don't matter. And I need to have your slope be 0, horizontal, when x is 0. And when x is 0, what axis are you on? You're on the y-axis. So I look up here, and pretty much there's two that have slopes of 0 on the y-axis, which is B and D. Okay, so I'm pretty much eliminating these three over here. And then I notice that it depends only on your x, and I look and I make sure I have parallel lines going in the vertical direction, which I do in all of these. And then I start going, okay, now let's talk about your slopes when x is positive. So for x greater than 0, all my slopes should be positive. I'm good there. I look over here and I go, wait a minute, if this equation, when x is greater than 0, would have positive slope, right there is a negative slope. Can't be that one, must be B. You can also kind of use your idea of, this one was one that we actually know the antiderivative of, that the antiderivative of x is going to be a parabola, and this is the one that sort of looks like a parabola too. Okay, but I'm just giving you all the little techniques that we're going to be looking at. All right, let's look at another one. Let's do D while I'm here, because the idea is I can kind of visualize the solution to this, and the solution, kind of as I sketch it in, what does that solution appear to look like? Kind of like a flip cosine. And so I'm looking for a trig function. I know that this depends only on x, and I need it to be a trig function because it's oscillating, and that's going to be that one right there. So we can pretty much get ourselves to this one. All right, so now our e to the x, that one should be obvious, because what's the antiderivative of e to the x? E to the x, which one over here looks like e to the x? So it would be here, and so on, all these little nice little e to the x transformations. So F is number 1. And let's see, now I'm left with the two harder ones, the ones that are dependent on x and y. Now, what I want to do is I look at this and I go, all right, let's talk about zero slopes. This one has a zero slope when x equals 0 and y doesn't equal 0. Okay? So this would be everywhere except for the origin, okay? And x equal to 0 would be on your y-axis. And if you look here, this one is going to, just by process of elimination, this does not have 0 slopes on the y-axis. This one appears to, because as I'm sketching then the little curves, you can kind of see that it kind of looks like it appears to have a min or a max here on that axis. You might also want to think about where you might have vertical tangents. Your vertical tangent in this case would be when y equals 0 and x is not equal to 0. And so we're looking at vertical tangents on the x-axis. And so again, you can kind of see here, you do look like as you come across, you have vertical tangents on the x-axis. This one, they kind of change going because it's 0, maybe 1, a little bit steeper going out that way. So clearly, this one right here is going to be C up here. Now, another thing to notice is to make a comment is that 0 over 0 has no slope. That is completely not a zero slope, not a vertical slope. That's your indeterminate form. There should be no slope point there, and they kind of have the ones on either side, but you'll notice they don't have it there. 0 over 0 has no slope at all. There should never be any segment of a tangent line drawn at a 0 over 0. Okay? And then by process of elimination, that leaves us with this. But just to kind of talk about this, you'll notice that like here, you have 0 slopes kind of on this diagonal. And when would your slope be 0 for this? It would be 0 when y equals x. Oh, that's your y equals x line. So you can kind of see that right there. And then you can play around with also paying attention to when x is bigger than y, okay? When x is bigger than y, you should have a positive slope, okay, in all of this fashion. But when x is smaller than y, you should have a negative slope. So you notice here's your y equals x line. And if y is bigger than x, notice all of this is negative slope. And then down here, all of this is positive slope, and that matches our part 5. So the idea is you just kind of work your way through, and you're really going to see most of these in the matching section. Example 7, just a real quick one again, just kind of going through this. Notice that this is a function of x only. Okay, so it only depends on the x. This is a function of y only depends on the y, and then these two depend on both. So I can pretty much scan through here and go here, this has every slope going across horizontally is the same. So this is only depending on the y, so pretty much this is going to be 2. Done. All right, and then I need to find one that has the slopes only depend on the x. So that would be part B. So this is going to be number 1. Notice I don't have to do much for that. I'm just looking for certain key features. Now here, looking for where the slopes, let's do this one. When would the slopes be 0? When y equals negative x, okay? So now look over here and you see that you've got this negative x line with your slopes of 0, and usually that's almost enough to do your matching. So this one would be 4. And then over here, this by process of elimination, this one looks like it would probably be that, but we can check when would you have slopes of 0, when x is 0 and y is not, so along the x-axis. Notice there's nothing drawn here at your origin, because that would be 0 over 0. You would get your vertical slopes when y is 0 and x is non-zero. And just kind of looking, if I were to draw in my solution, general solutions, they look like concentric circles. All right, and this is kind of little conic sections coming back. This negative x over y gave me a circle, but on the previous page when we had positive x over y, which was number 2, you look at this, what does this start to look like? Oh, that starts to look like hyperbolas. And so, and kind of talking about how the C is related, the C has to do with positives and negatives and whether it's a hyperbola that opens up or opens left or right, and kind of gives you the different branches that you're looking at. All right, let's come back to our examples over here, now that we've kind of worked with that. Slope field for a differential equation is shown at the right. Which statement is true for all solutions of the differential equation? All right, and we'll just do process of elimination. All right, number 1 says for all x less than 0, all the solutions are decreasing. Well, if I look over here and if I were to draw, say, a solution here, this solution appears to kind of be an increasing, but if I'm over here, then it would be kind of in a decreasing fashion. I would go with the answer that is no, because it depends on whether you're above or below the x-axis, but that's x less than 0 is both here and here. So we don't see, when we're looking at the slopes, what are we looking for? We're looking at slopes for x less than 0 that are all negative slopes. You have negative slopes here, but you do not have negative slopes there, so we can mark number 1 off, which means I can get rid of A and E in terms of my process of elimination. All solutions level off near the x-axis. You see that you have this little horizontal line indicated, which is an indication of asymptotic behavior. So, yep, I would say 2, we're okay. For y greater than 0, okay, so above, we want all solutions are increasing, which would mean all slopes are positive. So I look above here and I say, were all my slopes positive above? Yes. So that one is going to work, and so my final answer is going to be 2 and 3 only. All right, and so another example that you might see on your AP. Oh, example 9. We're looking at the slope field, and we want to know when you will have vertical segments. Okay, let's remind ourselves, vertical segments occur when you have a non-zero over a 0. So we need the bottom. This looks complicated, but it's really not a hard problem. We just need to go, I know that this is going to happen when 4x plus 2y equals 0, and the top, x squared y plus y squared, does not equal 0. That's what I'm basically looking for. If I solve this, just very quickly solve for y, subtract 4x, divide by 2, you would end up with y equals negative 2x. And the only time that this would not give me a vertical tangent line is if this makes the top 0. Now notice there are no never choices here. So we're pretty much almost done. And I can also see if I plug in negative 2x here, that I am not going to get a 0 automatically on that. So I'm pretty much going to go with my B. All right. So if they'd asked me where I would have horizontal line segments, I would need to solve and figure out where the top is equal to 0 and the bottom is non-zero. So that's all just practicing your knowing what your slopes are doing. Statements that are true, looking at example 10. We're talking about statements true about the solution of a differential equation whose slope field is shown here at the right. And so it says if your x is greater than 0, or if your x is 0 and your y is greater than 0. So x is 0, and so x is 0 is on the y-axis, and then I'm looking at y greater than 0. Okay, so these are all the points on the x-axis above the x-axis, or on the y-axis above the x-axis, and they want to say the limit as x goes to infinity of y of x approximately 0. So if I were to draw, so just kind of pick a representative one here, and if I were to draw in the solution that appears to kind of be what I'm looking for here, I would probably go with that. And I'm going, as x goes to infinity, these solutions appear to be going to infinity because of all these ups. So I'm going to say number 1, not going to work. So we can get rid of this one and this one. Let's look at part 2. All right, so here we're looking at the y values on the y-axis, because x equals 0, between negative 2 and 0. So I'm looking at solutions in between here. And if I start to eyeball in a solution here, kind of appears going to look like something along these lines. And the limit as x goes to infinity of this solution is going to be about negative 2. Do you have a horizontal asymptote? Yes, you do. So we're going to keep that one as a choice. So we can mark that off. And now I look at number 3, which is if I look at solutions that go through below, for the y values below negative 2, and then take a look at this, and trying to eyeball in your solution for that, all right, so pick, let's say this one, it appears to come up here and then across, and so the solutions would sort of look like that. And so the limit as x goes to infinity, does it have a horizontal asymptote of 0? The answer is no. So I would mark that one off, and then I would go with B for this one. All right, so now what I'm going to do, I'm going to kind of skip over a little bit and kind of look at something you might see on the AP in this set of notes, and then I'll leave the rest for you to kind of take a look at. Here, this was an actual AP question. They gave you a differential equation. Notice it depends on x and y. They asked you to sketch the slope field for the given differential equation. So let's do that fairly quickly. If I put in 0, I would get a slope of negative 1. So you kind of draw in your negative 1 slope. If I put in 1, 0, I would get a slope of negative 1/2. So let's think about this. This is negative 1. So I don't want to be more steep. I want to be less steep. So I'll kind of come in here, negative 1/2. If I have a slope, if I put in negative 1, 0, that would have a slope of negative 1/2. So this was negative 1/2, negative 1. So a little bit steeper than this. It's all relative. That's what you're looking at. Then we have, let's go up. Let's do 0, 1 would have a slope of 0. So let's put that in. And 0, 2 would have a slope of 1. So let's get that in, our slope of 1. 1, 1 would have a slope of 1/2. So same as that one, but going in the opposite direction. So we kind of go that way. My slope over here, negative 1, 1 would be negative a half plus 1, so negative a half. So same as that on that side, but going in the negative direction. Okay. Not quite, so it's kind of matching this one right here. And then our negative 1, 2, negative 1, 2 would be 1 minus half, 1 half. So that would be kind of in this fashion again, on there. And then our 1, 2, 1, 2, 2 minus 1, 1, 3 halves. So it's this one, but going in the positive direction. So you kind of get that in, not too bad. What are they going to look for? They're going to look for that you've got the horizontal, the zero slope in the right place. That's going to give you 1 point. And then the rest of them have to be relative to each other. Positives correct, negatives correct, and kind of a change in the size. So kind of get yourself there. That's an easy point to get. Now let's look at part B. Now we want to find the second derivative in terms of x and y. Now this is going to be important. Second derivative, really you just want to find the second derivative by taking the derivative of the first derivative. So here in part B, all I really need to do is, and since it's already solved for dy dx, I just need to take the derivative of this with respect to x. Derivative of 1 half x is 1 half. Your derivative of y is your dy dx, and your derivative of negative 1 is 0. But be careful, do not stop here, and that's why I was trying to highlight for you, in terms of x and y, you have to make sure that you get it in terms of x and y. Right now your second derivative is in terms of dy dx. You basically just need to substitute this back in. So our final answer to part B would be the second derivative with respect to x is going to be the 1 half plus, substitute back in your dy dx. 1 half x plus y minus 1. Now my second derivative is in terms of x and y, and you could simplify if you want to, but you can really just leave it there because this is the AP, and this would be my second derivative. So that takes care of the first part. And then it wants to describe the region in the plane which all the solution curves are concave up. Now let's remind ourselves, when are solutions concave up? Your solutions are going to be concave up. We'll kind of give them the reason. Solutions are concave up when your second derivative is greater than 0, right? That's your second derivative test. So we're going to tell them this, and we're like, well, when is that? Now I need to go ahead and simplify this. My second derivative is that 1 half x plus y, and then we have 1 half minus 1. So minus 1 half, I need that to be greater than 0. Okay? So basically all I have to do, usually they like you to solve this. I usually solve it for y since we're graphing an inequality in the plane. Y would be greater than negative 1 half x plus 1 half. So the solutions, the part of the plane that we're looking for, would be all the portion of the plane above the line negative 1 half x plus 1 half. Okay? So solutions are concave up for all above the line y equals negative 1 half x plus 1 half. Okay? So that was answer B. Now let's take a look at part C as our next. Now we want to know a particular solution to the differential equation. They're going to give me an initial condition, and they want to know, does f have a relative min, max, or neither at x equal to 0? Well, how do we find relative mins and maxes? You have to find your critical values, which are when the derivative equals 0. Okay, so critical values occur when your dy dx is equal to 0, and we have an equation for dy dx. which is our 1/2 x plus y minus 1/2 is equal to 0, okay? And that is equal to 0, okay, when y equals negative 1/2 x plus 1/2. And when does that happen? Notice they gave you an initial condition. Our initial condition was your dy dx evaluated at, and we want to go through the point 0, 1, 0, comma 1, which we already know, we already figured out, had a slope of 0. So at 0, comma 1 is our critical point that we are looking at, okay, which satisfies our negative 1/2 x plus 1/2. That if I were to put in, hold on a sec, let me see what I just did. I would call that a copy error. Come back in, this should be minus 1, because I had the first derivative. Somehow I got my second derivative in there. So my first derivative was my 1/2 x, double check, my first derivative is 1/2 x plus y minus 1. 1/2 x plus y minus 1 equal to 0, which would be, when I solve for y, negative 1/2 x plus 1. And you'll notice, okay, now that makes much more sense. When I plug in my 0 and my 1 for y, that's when you're going to end up with a slope of 0, okay? And that would be our 0.01, which we'd already calculated above. All right, so we have a critical value at 0, 1. But now, just being a critical value, having a horizontal slope there is not enough to make it a relative extrema. You either have to do the first derivative test or the second derivative test. First derivative test, you would have to test values to the left and the right, and that's really not what we're going to lean toward in this one. If you notice in B, since I found the second derivative, we're going to use the second derivative test. And so we're going to keep going, and we're going to basically go the second derivative evaluated at my 0, 1, my critical value, is going to equal, if I plug into my second derivative, 0 for x, 1 for y, we're going to get 1/2. The important part of that is greater than 0. And when the second derivative is greater than 0, what does that tell you about your curve? At that point, the curve is horizontal tangent and it is concave up, which is a relative min. So we can make our conclusion. There is a relative min at the point 0, 1, since at that point dy dx was equal to 0, and the second derivative, dy dx squared, is greater than 0. And the reason is because of the second derivative test. All right, does that answer everything I need in C? And we've justified, okay? So we're good with part C. And then now in part D, it has to do with, you want to find the values of the constants, m and b, for which the solution to the differential equation is linear, y equals mx plus b. Well, the first thing you want to recognize is that you actually did work for this. We pretty much determined that the solutions were concave up when you were greater than this line. They were concave down by the opposite when you are below that line, and when you are on that line, you basically have a curvature of 0, and that's basically what they're asking for there. They're basically saying, when would you have a linear solution? You have a linear solution when your second derivative is 0. Okay, so y equals mx plus b is a solution when your second derivative is equal to 0. And you'll recognize you already did the work, and that would basically be when your negative 1/2 x minus 1/2 is equal to y. that is when you would get your derivative equal to 0. Just basically replace that up there. Recognizing that's the place where you switch from being concave up solutions above this line right here, okay, and concave down solutions when you are below the line, and when you're on the line, then that is going to be your linear solution. So make sure you answer the question, because they ask you to, don't just infer they'll know what M and B are. They want you to find the values of M and B. So solution is y equals mx plus b when m equals -1/2 and b equals, do I have that right when I solved it over? As a plus and 1/2. And then we're done with that. So that's an example of what you're going to see for a free response type problem on the AP. I will leave you to go ahead and do example 11 on your own, and let's see, what else do we have on here? Example 13 would be another good one to take a look at. And example 14, I will leave that for you. I'll put some solutions up for you for these. When you get to this last page, don't worry about example 15. That was on a BC test, so you can kind of skip over that. And you don't need to worry about example 16. All right, so what I would like for you to do definitely is to finish the examples that are in this set of notes. I have also put up a worksheet to this. I am going to make the worksheet optional. It's some extra practice for you, but I think that this slope field idea is easy enough that as long as you complete the examples in this packet, the worksheet's there if you want to do some extra examples, but I'm going to leave that as an optional assignment for you to do. The key is also up there, so you can do that as you prepare for the AP.